Determine how many terms of the following converging series must be summed to be sure that the remainder is less than 10 to the negative fourth in magnitude. Okay, so here's our series from k equals 0 to infinity, 7 times negative 1 to the k power over k factorial. Okay, and we're told that let the series from k equals 1 to infinity times negative 1 to the k plus 1 times a sub k, let it be a convergent alternating series with terms that are non-increasing in magnitude, and let r sub n, which is the remainder, equal to s, which is the sum, minus the sum of n terms, however many terms that we decide are needed in order to get that remainder. Be the remainder and approximating the value of that series by the sum of its first n terms. Okay, so if that's true, then the absolute value of the remainder is less than or equal to a sub n plus 1. In other words, the magnitude of the remainder is less than or equal to the magnitude of the first neglected term, the first term after the term that we choose. Okay, so how we're going to tackle this problem is we want to make this series look like this. Okay, so there's a couple changes that we have to make here. We can't start at 0, we need to start at 1. Okay, and our exponent here has to be k plus 1. Okay, so here's how we're going to do that. We're going to do a substitution. We're going to say that k is going to be equal to m minus 1. Okay, so if we say that k is equal to m minus 1, I can plug in everywhere into this. Everywhere I see a k, I can put an m minus 1. So I get the series from m minus 1 equals 0 to infinity of, let's see, 7 times parentheses negative 1. Instead of a k, I put an m minus 1 divided by m minus 1 factorial. Okay, so that's starting to look close to this, but we're not quite there yet. We did manage to make some changes. Let's see what those changes did. So we can actually move this 1 over to the other side on our next step. Okay, so that will be equal to m equals 1, which is kind of like this, k equals 1, to infinity. And then we have not much here that I can do yet to change this. We're going to take care of that exponent here in a second. Okay, so we've started at 1, just like the formula said, but our exponent on the negative 1 is m minus 1 instead of k plus 1. Okay, so the letter doesn't necessarily matter. It doesn't matter. But we need this to be a plus 1. So instead of an m minus 1, we need it to be m plus 1. So if you know about what's happening here, this negative 1 is getting raised to these powers, and they're either going to be odd or even powers, which means that's why it's an alternating series. They'll either be positive or negative. But you can take the negative 1 to the m minus 1, and you can say that that's equal to negative 1 to the m plus 1 times negative 1 to the negative 2. Okay, so that might take a second to take a look at that and make sure that you trust that that's true. If I combine these two back together, I would get m plus 1 minus 2. Plus 1 minus 2 would be negative 1. So this is true. Okay, the statement is true. But what is this? Well, negative 1 to the negative 2 power is the same thing as 1 over negative 1 to the positive 2 power, which is 1 over 1, which is 1. Okay, so what we can basically do, given that we know this, is that we can just change this to a plus 1, and we won't be changing anything about it, about the actual series. Okay, so I'm going to go ahead and do that. So I get m equals 1 to infinity of 7 times negative 1 to the m plus 1 divided by m minus 1 factorial. Okay, so we've got the negative 1 raised to the m plus 1, which is like this, negative 1 raised to the k plus 1, and we're also starting the series at 1, just like this. So we've got it pretty much done. So if we do that, what's our a sub k? And we'll call it a sub m instead of k, since we're dealing with m. Okay, so it'll be, let me write it where you can see it, m equals 1 to infinity of 7 over m minus 1 factorial times negative 1 to the m plus 1. Okay, so this is our a sub k or a sub m, whatever you want to call it, and this is that negative 1 getting raised to the power. Okay, so what it said is that we want this, our a sub m, which is 7 over m minus 1 factorial. If we have the next term, which is a sub n plus 1, let's see, what would that be if I have a sub n plus 1? We could exchange, instead of an m, I could write an n plus 1. So it would be 7 over n plus 1 minus 1 factorial. And the plus 1 minus 1 just turns into just an n on bottom, n factorial. Okay, we want that to be less than 10 to the negative 4. Okay, so this is what we're trying to solve right here to see how many terms that we need. Okay, so let's solve that. 7 over n factorial is less than 10 to the negative 4. Okay, so that is 7 over n factorial is less than 1 over 10 to the 4 factorial, or 10 to the 4 power. Okay, if I cross multiply, I get 7 times 10 to the 4th is less than n factorial. Now, you can multiply that out. That's going to be 70,000 is less than n factorial. So I need to figure out what number do I plug into n such that it's more than 70,000. Okay, so let me write a few of the factorials out here. So 1 factorial is equal to 1, 2 factorial is equal to 2, 3 factorial is equal to 6, 4 factorial is equal to 24, 5 factorial is equal to 120, 6 factorial is equal to 720, 7 factorial is equal to 5040, whoops, comma in the wrong place there, 5040, 8 factorial is equal to 40,320, getting close, and 9 factorial is equal to 362,880. So we don't need to go any farther because we know that 9 factorial is going to be more than this, more than 70,000. So if n is equal to 9, then this is true. So the original problem is asking you how many terms of the following series must be summed to be sure that the remainder is less than 10 to the 4th. Okay, so this solves that problem. We need 9 terms. Okay, if we have 9 terms, then the next term, if we plugged in here, okay, if we plugged in a 10 right here, then it would be way less than 10 to the negative 4. 7 divided by 10 factorial is way less than 10 to the negative 4. So our answer for this is that it is 9 terms to get us the remainder we want.